So in this side, the nitrogen is mentioned here. So a nitrogen gas is mentioned here, that you should not forget. So on to this side here, a nitrogen, that is the volume is mentioned. Nitrogen is contained in the cylinder behind a piston is initially at a pressure and temperature, but the gas is compressed isothermally and reversibly until the pressure is this one. So drawing the PV plane and TS planes are very important. So this is the compression, isothermal compression, that is 1 to 2. Isothermal means PV is equal to constant, and observe the directions. PV, TS. Isothermal compression means this is 1 to 2, where the temperature remains constant. So here one has to be more careful about this gas usage. That means here the molecular weight of the nitrogen is given. So the R value, that is the gas constant. So this R is nothing but equal to gas constant. So this gas constant, one has to be more careful about this universal gas constant divided by molecular weight. So the universal gas constant, it is 8314, standard value 8314, divided by molecular weight is 28, this one. So you will get this value as 297 joule per kg, joule per Kelvin, kg Kelvin, joule per kg Kelvin. Sometimes you can get the carbon dioxide gas. The molecular weight for the carbon dioxide is 44. Sometimes you can get the carbon monoxide. Sometimes you can get the helium, right? Now here also you should have to observe that whether it is a monoatomic gas or it is a diatomic gas or it is a triatomic gas. If air is given, then you have to assume it as a diatomic gas. Diatomic gas where gamma is equal to 1.4. If for a triatomic gas, gamma is 1.27 to 1.3. For a monoatomic gas, then gamma is equal to 1.67. Example is helium, neon, right? 1.67 monoatomic gas. Because here, when you are going to observe this PV to the power of gamma is equal to constant, whether this particular gamma is for monoatomic gas or diatomic gas or triatomic gas, that they should be more careful about this one. Once this R is over, then you can find out that M is equal to PV by RT. Then if you can make the calculation P1 V1 by RT1, you can get the value as the 0.0491 kg. Then the change in entropy, that is S2 minus S1, is equal to mR ln P1 by P2. mR ln P1 by P2. So that is minus 0.02216 kilojoule per Kelvin. So this is what the formula you have to apply here, because it is a isothermal process. So that is the first one. And what about the heat rejected? So this heat rejected is equal to T into S2 minus S1. T into S2 minus S1. So here it is, they have asked that calculate the entropy, the heat flow, right? So the entropy is over. Second one is the heat flow. Q is equal to T into S2 minus S1. So you will get this one as the 6.382 kilojoule. 382 kilojoule. So for an isothermal process, delta U is equal to 0, because it is mCV T2 minus T1. So T1 is equal to T2 so that it is 0. Then from this case, apply the third, because here Q is equal to delta U plus W, but this is 0. So finally that Q is equal to W is equal to 6.382 kilojoules, 6.382 kilojoules. So that is how a student has to work the problems like this one. So this is one type of a problem. That means other than the air, gas. So one problem is picked up. So so far entropy changes for solids is worked out. Entropy change for liquids is worked out. Entropy change for air is worked out. Entropy change other than the air is also worked out. And the entropy changes specifically applied for the process. Entropy change applied for the cycles also. Entropy change for the cycles also, some of the problems which are worked out. Now there is one more problem that a block of iron weighing 100 kg, block of a iron weighing 100 kg, having a temperature of 100 degrees centigrade, 100 degrees centigrade, is immersed in 50 kg of water, immersed in 50 kg of water, block of iron weighing 100 kg and having a temperature of So what will be the change of entropy of a combined system of iron water? I think this problem has repeated. So try to observe this case. So I will move on to the other problem. So moving on to the other case. Here a reversible engine is mentioned. A reversible engine is mentioned. So the reversible engine here three things are given. Three sources are given. That is the T1, that is 200 Kelvin, 300 Kelvin, 400 Kelvin, taking the heat Q3, Q2, and this Q1 is 5 megajoules, and the net work output is 840 kilojoules. So a reversible engine during the cycle of operations draws 5 megajoules of heat from 400 reservoir and does 840 kilojoules of work. Find the amount and the direction of heat interaction with the other reservoirs. So first, assuming that this Q2 is positive and assume Q3 is also positive. Later, after finding the values of Q2 and T3, then you can get the things whether it is positive or negative, the assumption is correct or not. So later you can get it. So according to the first case, that is the entropy change. So the entropy change, that is the ds is equal to Q by T. So in connection with this one, that is in a cycle, What is the formula you can get? One is that is Q3 divided by 200 Kelvin plus Q2 divided by 300 Kelvin plus 5000 kilojoules. So all these things are in, so this is kilojoules. So this is equal to 5000 kilojoules divided by 400 divided by 400. So you can get it as a Q3 by 2 plus Q2 by 3 plus 5000 divided by 4. This is the first equation. That is the first equation. Then second one, in the second case, you just focus on to this one. So in the second case, that is the second case, it is Q3 plus Q2 plus 5000 kilojoules minus W. So the total network here it is 840 is equal to 0. So solving 1 and 2, you can get the values of here. Q2 you can get the value as minus 4980 kilojoules, and Q3 value will get it as 820 kilojoules. So the assumption for this one is wrong. That means here you have to go for in this direction. So here it is minus 4980, but Q3 is correct. That is 820 kilojoules. That it is correct, right? So that is one way. So that is one case, and second one is so this is one type of a model problem. Sometimes you can get the problems like this model also. So I have covered all the kinds of a model. So here let an iron block of weighing. So here the heat lost by the iron block is nothing but equal to heat gained by the water that you have to apply. So quickly I will go through that one here. That is heat lost by the iron block. So heat lost by iron block, energy equation you have to apply, is equal to heat gained by the water. So when you get this particular thing in your mind, then you can easily solve. That is, this is 100, and the specific heat it is for iron, the specific heat is 0.45, and the temperatures, that is the final temperature, and this is what you need to find, is equal to heat gained by the water, it is 4.18 TF minus it is the 20 degree centigrade. So with this one, where you could be able to get the TF value is 34.17 degree centigrade. Then the change in entropy is equal to change in entropy of the iron, that is one is going to become the system and one is going to become the surroundings, that is water. So substituting the numerical values, so that is the MC ln, this is now here you have got, it is 34 plus 273, it is 307.17 divided by 373 plus 50 into 4.18 ln 307.17 divided by 293 is equal to 1.1355 kilojoule per Kelvin. So this is how you can get the answers, right? So one has to work onto this particular type of a problem. So that is the heat lost by is equal to heat gain. From that one where you could get the final temperature, and once after getting the final temperature, then the remaining things you can sort it out. So this is one model. So last one, I'm going to cover the one model, that is the final case. So calculate the entropy change of the universe as a result of the following process. So it is also covered in terms of iron block problem, but here it is one more, that is the copper block. It is placed in a lake at 8 degrees centigrade. The same block at 8 degrees centigrade is dropped from a height of 100 meters into the lake. Then two such blocks are joined at 100 and 0 degrees centigrade are joined together. Then what is the answer, right? So that is here. The first case is the entropy change of the copper, that is equal to, which is from, what is the lower temperature, that is from the lower temperature is 8, it is 100, that is from 100 degrees centigrade into, that is the initial is 100. So 100 means 373, 8 278 means it is 281 kelvins, mc dt by t. So after solving this one, it is the copper block mass is because the heat is leaving here, so that is equal to, it is the joule heat capacity is already given. So this is nothing but equal to mc heat capacity, 150 ln 281 divided by 373. You will get it as a minus 42.48 joule per Kelvin, right? Next, entropy change of the lake. So that is the specific heat of the lake into, it is going to change. That is here you have to apply it as a Q by T. So Q is mc delta T. So 100 minus 8 divided by 281. What is this Cp here? This Cp is nothing but equal to the same, that is mc into 100 minus 8 divided by 281. So that is nothing but equal to 150 100 minus 8 divided by 281. So you will get this one as a 49.11 joule per Kelvin. So the entropy of the universe is equal to entropy of the copper plus entropy of the lake. So the change in entropy of the universe is equal to change in entropy of the copper plus change in entropy of the lake. You can get as 6.63 joule per Kelvin, right? So this is the A bit. Then work it out for the second case. What is the second case? The same block, but it is dropped. It is dropped from a height of 100 meters. The same copper block is dropping at some height. So the potential energy is going to come into this picture. Potential energy is going to come into this picture. That is in this particular case. So on this case, the second bit, The second bit, change in entropy of the copper. Change in entropy of the copper is equal to 0. Then change in entropy of the lake is equal to W, that is nothing but equal to Q by T. So what is that particular Q value here? That Q value, it is mgh. The potential energy will be converted to the heat energy. So you will get that value as 588.6 divided by the temperature of the lake is 281. So it is 2.09466 joule per Kelvin. So the copper block is 0. Now here entropy change of the universe. So entropy change of the copper plus entropy change of the lake. So you can get it as 2.0946 joule per Kelvin. So the same value you can get it. So this is the second bit. Then the third bit, what is the third one? Two such blocks at 100 degrees centigrade and 0 degrees centigrade are joined. So that means here you need to find out the average temperature. So that the final temperature, that is the average temperature, that is the C bit, is equal to 100 plus 0 divided by 2. It is 50 degrees centigrade. It is 50 degrees centigrade. That is 323 Kelvin. Now change in entropy of the copper block is equal to again MCP. So T1 to T2, and this is dt by T, and this is nothing but 50 degrees centigrade, that is 323 Kelvin. And the second one is change in entropy of the water. So this also you should have to carry out. And in another words, you can also carry out change in entropy of the universe is equal to specific heat is constant ln 323 divided by 373 plus ln 323 for water by 273, and this is equal to 3.68638, that is 3.64 joule per Kelvin. So this is how you can also solve this particular case, right? So here the idea is that what you have to get is specific, that is a heat capacity, MC, heat capacity for iron block is equal to the heat capacity for water. This you should have to get the idea. Then you can proceed to solve the remaining cases, right? So hope this particular things are clear. Then all the models, it is covered in entropy point of view. So whatever the things are required at the first year level and at the second year level, then these concepts are clear. Thank you for listening this video lecture.